Jeremy Freeman. I'm one of the organizers here, and I have the pleasure of introducing Wayne Thompson from SAS for an industry keynote this morning. He's going to help us learn about machine learning we didn't learn in school. Thank you.
My pleasure to be here today. Thank you for that applause. It's such a beautiful university. Hope to get on the campus a little bit later this afternoon. So I've got a fun topic. A lot of it's common sense. But I've been doing machine learning for about 26 years. And kind of like the Travelers commercial, I think I've seen it and I've covered it. So I want to really kind of go over some things that you might not have learned in school. And by the way, this is a hot topic. I go to lots of conferences, especially in San Francisco. Headed out to one, it's called Open Data Science West in San Francisco in a couple weeks. Everybody is talking about machine learning ops. Amazon, Google, Microsoft, H2O, DataRobot, and of course SAS. And we've been doing it for a while. We call it the analytical life cycle about a couple decades ago. And MLOps, of course, comes from DevOps. And it's all around the continuous development and improvement of machine learning models. And some people also refer to it as AI ops or even just model ops. And I want to drill into this getting your data integrated like we saw in the talk earlier today about data integration with active learning. That was really cool. Building models and putting those models to work. When I actually came to SAS, I thought I would be talking about the latest auto-tuning techniques, looking at the latest algorithms like Cat Boost. But to be honest, most of the customers don't have a problem building machine learning models. They have a problem putting the models into production. And it's a real issue. Let me give you an example of someone who does a really good job of this. How many soccer fans do we have out here? Okay, we call those football fans. You know. And I come from the University of Tennessee where we used to have a football team. And I hear that the American women have a football team. I'm not so sure about the men. We don't have much of a U.S. men's football team. But this company is called SAI Sports. They're a development partner of SAS. And I've been working with them along with a lot of smart people. And by the way, SAI Sports are the real smart people. This is their application, not a SAS application. And they're in sports analytics, and they track these football players, and they don't use sensors. A lot of the players don't like to wear sensors. And they do it through computer vision. Why are they doing this? Has anybody heard of Vinicius Jones? Well, he got a transfer. That's when you get traded, is the terminology in football. You know better than I. I'm an American football fan. About those Cowboys. And he got transferred from Flamengo to Real Madrid. How much money do you think he made? $50 million. He was 16 years old. Okay? So this is big money. It's a big money sport. So what really, in the bottom line, SAI Sports tries to do is they try to evaluate these players based upon monitoring them in real time with object detection models at 50 frames per second. And through this, using a YOLO model, YOLO version 2 to be precise. By the way, that's got 46 million parameters, roughly. Roughly. Have you deployed a model with 46 million parameters? That's common in deep learning now. And a lot of people struggle with that. And they're not only deploying these models, but they're putting them into SAS Event Stream Processing Engine. And then we wrote an API directly into 14 cameras around the pitch. Okay, they got 14 of these cameras in all these big stadiums in Europe. And they're monitoring these players and using this you only look once hotshot deep learning model to not only track the player, the ball, and their competitive advantage is they actually track all players, not just the player with the ball. Let me give you a feel for what, and this is a very early video when I first started with them. Let me just give you a feel for what they're doing. The application is called Ball James. Anybody ever heard of Bill James before? Bill James is from the Oakland Athletics, Moneyball. And so they are truly a sports analytics company. And again, they're looking at player position. They have a tough time actually tracking and picking out the goalies because they're constantly changing uniforms and so forth. And they're doing this at 50 frames per second and putting this into the event stream processing engine. This is a company that lives on deployment. That is their business model, totally. So why don't other companies get this right? Can you guys hear me okay in the back? And my style is really laid back. So if you got a question or you want to talk to me about anything at any time, just ask. You want to enforce or some kind of comment I make, just speak up. And I kind of like to join you. I don't like to stand up here and kind of be corralled on that podium. It's not my style. So putting models into production is a pain in the behind for most organizations. I don't really get it. Analytics is not that hard. I truly don't believe analytics is really that hard. We should do better than getting only just under 47% roughly of our models deployed. That's not a good number. We should be up around 80 to 90%. So, why do you guys think models don't get deployed? Just give me some kind of thought, first of all. Okay, something about security, I heard. Okay, first of all, deploying models is like dogs and cats. They can cohabitate. I have a dog and a cat at home, and they do just fine together. But IT and data scientists or statisticians typically have problems working together. That is probably the biggest reason, in my opinion, why machine learning models don't get deployed. Because the data engineer, and it's not just going to be you and your research effort putting this data together. You're going to be working with very large operational data, and you have to really not only regularize your models, but you have to regularize the deployment of those models. And so in this process, and I think you all are aware of it, I don't need to go over every bit of this with you. You've got to define a business objective, a research objective. You guys got that covered. You're good at that. And then you have to prepare historical data. And one thing I find out is, you have to do some data quality analysis. And how you label the data is really, really important. I was involved in a fairly big project, drinking our own champagne at SAS. And the marketing people labeled data for whether or not you're a lead or not. Marketing's supposed to give sales leads. Everybody thinks at SAS their function is to produce white papers and get up and do talks like this, but their goal is to provide sales with leads. Well, I got the data, and I built a gradient boosting model. I work with the optimization team to do multi-objective optimization, where we optimize concurrently the overall misclassification rate and also the false negative, because I didn't want to give a lot of leads to sales and them not being leads. They get mad. They get really mad about that. But the data was labeled poorly. They just created a bunch of business rules. Like, if you attend a SANSI event and you walk over to that booth, you're likely to buy SAS software. That's a rule. And so with machine learning today, I can use some kind of heuristic kind of rule finding algorithm and pull those rules out of the data that were defined by the marketing people, but it just doesn't generalize. So think about that data quality, leakage, and all these things. And then you kind of let the data scientist, she goes to work. She goes to work here. She actually does the transformations, does all that with the features, and then because you've got this blown out table with all these records and all of these columns, you got to do some dimension reduction. Then you build your model. Then you evaluate your model. And hopefully you're evaluating your model on test data. And so many software packages I see out now go like this. Oh, I'm going to take 60% for training. I'm going to take 30% for validation. Now, what's validation data? I'm going to peek at the training data while I'm fitting it and try not to overfit. Then they take 10% for the test data. We got big data these days. So first of all, get really big test data. Too many of these things are done like a Kaggle competition today. The issue is we're trying to fit so much of this data, and just by random, eventually one of these models is going to generalize on that little teeny test data set, just by chance alone. Time after time after time after time, I see data scientists, really good data scientists, they think, do that. If you've got test data, get that test data as big as possible. You will get good models because it is the population that you're trying to do inferencing. And if you build a crappy model, put your favorite word in for crappy, then you're not going to do very good on inferencing. Simple as that. Then you have to serve the model. That's a terminology, that's kind of a West Coast terminology now. When everybody says score a model on unseen data, you know, at Google, they'll talk about serving a model. And so that's just deploying it. And that's where the data scientist may be involved, but that's where actually the data engineer, the IT scoring officer gets engaged. Actually, I think that's where the test data ought to be checked, right there, at that point. Let that be not only, and in credit risk, they do that because people in credit risk have been doing models like this with a lot of red tape around them for many, many years. Go look at something called OCC-2016. This bulletin provides all the guidelines for how you should deploy machine learning models because they have regulators that come in and said, show me your model. I want to see how it was developed. What are the inputs? What are the turn down codes? Did you do reject inference? And so I think actually that should be done by an independent model validation specialist if you can afford it. Definitely an organization like Chase or HSBC or Target. Then you actually monitor the model because, of course, all models degrade. As soon as they're put into production, they tend not to get better, they tend to get worse. And I'll go over some model monitoring statistics with you. Before I go on with this, how many people here use Python? Aha! How many people, and I'm a data scientist, I like to get some data. So it's my chance to get some data. How many people use R? So I saw some double hands there, so that's cool. You roll some R and you sling some Python. How many use SAS? Not that many. Just for the hell of it, I'll do this. I'll go back to that slide. What is this? This is an HTML5 from a Jupyter notebook that I developed. And I'm importing some packages that you're very familiar with. But what's this thing called SWAT? Well, first of all, SWAT is what you get when you let developers name things. It stands for SAS Wrapper for Analytical Transfer. Okay? So you're sitting here and you've got your Jupyter notebook and you're creating Panda data frames, and then all of a sudden you make a connection to a SAS MPP server. It could be a GPU if you're doing deep learning. And so what it does is it sends instructions over to SAS, And it does all the computations there, and then it brings back results to your Jupyter client. Works the same way with RStudio. So each and every one of you here, I probably shouldn't be showing my server name up here. We do have some good cyber security at SAS. But in this example, and this is actually a colleague of mine in the deep learning group, this is where we're loading some of this football data. And we're going to load it and we're going to lift it into memory. And it looks very Pythonic, doesn't it? You have the name of a data source, the library, then I'm going to read it in. And you see things like num rows. I'm going to apply a where clause. I'm going to provide a filter because I only want to read in certain images. But I'll get down to the part that some of you probably do just for kicks. I'm going to define my targets. I'm going to set the bounding box. I'm going to set the center of the bounding box. And I'm going to do some extraction for the images. I'm going to change the color channel for them. All I'm trying to do is show that you can use SAS with Python. And you've spent a lot of time investing in Python. And try some of this out. We'll talk about that on the side. How we doing? Okay? I've got big shoes to fill here. I'm the keynote. Jeez. Didn't get any sleep last night. What's one thing we can do to help ensure success? Okay, I want you guys all to become farmers at these big organizations. I want you to start harvesting machine learning models. That means you got to get serious about your data integration processes. Anybody heard of Cabela's? They call it the kitchen sink. That's this master or set of master analytical based tables that they use, and they build all these purchase propensity models off of it. Not one, but hundreds. Turkcell, very large customer in Turkey. They have 600 labels. And those labels are separate targets. And they use the same underlying feature set and build those models monthly. Almost like a Henry Ford type situation. That means you've got to go to the cloud, to your S3 buckets. That means you got to go to your Teradata relational database. You got to go out to all your Hive files, et cetera, and you got to standardize that and get a blueprint. And that, first of all, helps cats and dogs cohabitate. Now there's a mistake with this because I worked with Chase and we worked on getting at Chase, they're a big company. Big, huge analytical company. Miles and miles of just Ohio State partition cubicles. Everybody's an Ohio State fan there. They're in Columbus. And what we needed to do, though, is we started to make this such a farming type exercise, a harvesting exercise, but please do not handcuff the data scientist. Don't do that. Because I'm fine with auto machine learning. I'm not a huge fan of automated modeling, first of all. Probably an abnormality there. If you want to do some harvesting, Cisco builds 3,000 machine learning models per quarter. They got to do what's on the left to be able to do that. But if you build a cybersecurity model, because I gave you the name of my server, I've got to go out and retrain and rebuild that model perhaps daily. And I've got to get to the detailed data. I've got to do some pioneering on top of harvesting to be able to build these models effectively. So it's important to make sure the data scientists can get to the detailed data records. I'm talking about the call center. I'm talking about the custom verbatas. What your customer is saying is highly predictive. I'm talking about all the transactional data. That is the heartbeat of the customer. If they're not getting to the transactional data, you are building a shitty model. I can guarantee it. Okay, this one is obvious, so I'm not going to say a lot about this. But the real key in machine learning is feature engineering. And I'm not talking about automated feature engineering. I'm talking about up here feature engineering. Understanding the business. Understanding the relationship between these variables. You are scientists. You get that. Out in the commercial world, they don't get that. I'm just going to run a bunch of box-Cox transformations and take the inverse of this and that and try to build a model. And if I use something like imputation, a lot of times in medical industry, I'd rather take, if somebody's trying to get my weight, I would rather use the information about me to predict that my weight is 249 pounds versus the average in this room. The average wouldn't be a very good estimate. Now, this is some things that you probably know, but many of you have forgotten or you don't practice. That's the part of this talk that I kind of stuck in at the end because, again, I started seeing so many people forget what they learned in school. Generalization is what counts. We already talked about it. You're going to take historical data here, and you're going to inference on unseen data. That's the goal. First of all, Occam's razor. Anybody know where that came from? It was a monk. And this monk said, you need to defend your hypothesis with as few of elements possible to get that hypothesis correct. And so what I'm saying here is Occam's razor says build parsimonious models. Build as simple models as possible that generalize well. What Capital One will do is they will build an extreme gradient boosting model. And they will get a C statistic, or they will get a KS statistic. They will get some kind of error rate on holdout data. And then they will work their logistic regression model up to that. Logistic regression is still the queen of machine learning. I see it more than any other model type out there. And people are applying for credit. Their models have to be interpretable. I'm not sure that Lime is going to work with the gradient boosting model with the feds yet. Those people that come in and check your model. And so they work on getting interactions and feature engineering to get those models up there. And then a few things about overfitting. We've got the blue circles, that's the data. This green line is some kind of line that we could never obtain. It's the kind of real surface to that nonlinear function. And then the red line is what you fit. And with overfitting, we might want to look at fewer features. We might want to get more data. Down here at the bottom, for bias, obviously variance and bias, where do those terms come from? Statistics. I'm a statistician by nature, and machine learning definitely borrows a lot from statistics, by the way. And so here, getting more data for high bias probably won't help, but getting more features likely will. Good features. And fitting perhaps more complex models might also help. Now I'm kind of saying one thing and then another. I'm saying build simple models, but now I'm telling you to ensemble the models. I like to ensemble, especially when my data is not that big. Because small perturbations in the data, if you continually ensemble those, that's going to help you with your modeling. I'm not a huge fan of building blenders and ensembles on training data sets that I often work with, which are definitely going to be bigger than 1 million observations. I don't see anything smaller than that, unless it's a computer vision problem. We're doing okay on time? Okay, excellent. The last thing I want to say on this slide, sampling is not dead. I hear that at SAS all the time. Everybody says, well, you just model all the data. Well, 9 times out of 10, I have a rare event. I have an event that's less than 1% or around 1%. The target event, like fraud. Even customer purchase propensity for many of these organizations like Cabela is going to be around 1 to 2%. So I always try to undersample the non-event, oversample the event, and I do that doing different ratios. I'll fit like, if I have a 1% event, I'll fit like 10% of the data, 10% event, 20% event, 30, 40, 50, and then ensemble that. I held a Shark Week contest at SAS with some really good data scientists that worked for me at the time. And that worked really, really well for predicting rare events. Intelligent sampling is not dead, especially in the case of rare events. Okay. Let's talk about some types of scoring, just so you have a feel for that. And a lot of the rest of this is somewhat common sense. Batch scoring, still very prevalent. Batch scoring, what State Farm will do is they got all of their policyholders, and they will score every one of those policyholders every day in batch. That way they have a good estimate for claim adjusting. You know, they want to set rates that are fair yet profitable. And they use C-scoring in this case from SAS to score the models directly in DB2, at least at the time they did. And they do all this other scoring, but this is a very typical way to score all the records. This is more common today. If I go and I'm Capital One and I go to a website and I apply for a credit card, I put in my name, my address, I put in things like my salary, how long I've worked at SAS, that's a long time. And then boom, it takes that, it maps it to the model, and I get instantaneously, I was accepted for credit. Now, if I was rejected, they're probably going to send me to somebody. They're not just going to say no. But that's an example of a web service where it just calls the model and brings back on a per record basis. That's the most predominant type of scoring. I think the future of a lot of machine learning is in these two buckets. I'll go ahead and show them both for the photo. But online scoring. What is SI Sports doing? They're scoring. They have those 14 cameras around the pitch. They got that YOLO model, and they're scoring at the edge as the data is being collected. All IoT applications. This is the future, I think, of how we want to implement modeling and inferencing. Training offline is fine, but if we can move more of that training to inline, that's going to be even better. And what I call automated modeling is different from what others call automated modeling. To me, automated modeling is that I run the entire pipeline model in place as the data is being collected, and I derive a brand new model on the fly. I don't know anybody that does that very well yet. Great research opportunity. Most of our algorithms are multi-pass. How the hell are you going to do that? Most of our algorithms read the data many, many times to solve some kind of objective. So we have to be careful and figure out how to do that. At SAS, we've got some really cool things. We can train that model like SI Sports did, offline. Then we can put it into the scoring in real time. But what I want to do and focus more on is this. This is where SAS is kind of ahead of the pack, in my opinion. The primary area. These are all the things that we do. Okay, online scoring, that's where I develop the model offline, because I have to. You're not going to fit some deep learning model, like an RNN, as the data is being collected. You might save state, retrain, save state, retrain, save off your weights, retrain. Same thing with a gradient boosting model. But look at all these things that we can do. A recommendation system. You can plug collaborative filtering right into the data. As you're clicking around on Amazon, it should understand you as a user, the items that you like, and make those recommendations in real time. We do that today. And the same thing too with DB scan. That's a nice clustering technique. Very nice technique. I'm good. So a lot of these things I'm really excited about and hope that I see some of that in your research. These are the steps for model management. They're kind of, I think, fairly obvious. You know, once you get the model registered from the data scientist, you schedule it and run a scoring test. You make sure that the inputs and outputs, because what was used in training has to be available at the time the model's scored. So you need to run independent scoring tests. And then at some point the model goes afoul. What do I mean by that? Classical concept drift typically says there's a change in the y, but not necessarily a change in the x's. As I said, though, all models start to decay. You need to monitor those, collecting data as you're getting it, and almost have a dashboard around your data, even for your scientific research. You know, because many of you are collaborating with other developers studying the same topic. I actually was a scientist in my PhD, and we did mixed models on grazing trials, and we collaborated with lots of other people, and we merged our results into metadata analysis, and then we monitored it over time. Some things you can do, I didn't write out the formula for these, but you can look them up. These all come from credit risk, by the way. People like Dina Duhan at Canadian Imperial Bank of Commerce, or Kevin Cooper at Ford Motor Credit. Population Stability Index says, how does the Y change? And it's basically like a chi-square test, and you're just measuring shifts in your predicted values. What is a characteristic? A characteristic, and I got 2 more minutes, I'm going to quit. A characteristic, what they do when they build credit scorecards is they bin all the data. Why do they bin the data? Because they need to create points. You have a FICO scorecard, for example. And so each feature is actually called a characteristic. That's where that name comes from. And then the bins themselves are called attributes. And the characteristic analysis then says, well, what are the changes in the features over time? And then you need to do just some plain old good-fashioned, like least square means, if you would, on the various treatments and check the outcomes. Fit some least square means or something like that on the data. Do some analysis of variance. And then you also want to look at the model performance itself. So refit the model, check what the model lift is. What's the capture rate of the model? That's lift. What's the ROC, or the C statistic? Okay? Cumulative accuracy profile that helps you distribute between 2 or more populations, 2 or more models. And this is good work for some of you going forward. How are we going to really monitor text analytics? Jim Cox is here. He's an expert in text analytics. It looks to me like you could get polarity if you're doing sentiment and monitor shifts in polarity across time. But there's not just supervised machine learning models. There's all types of models that need to be monitored. And the number of reports out there in the literature are very small. There's a great research opportunity for developers at SAS, for example, to come up with some good metrics. And we've got some experts in the back. Brett Wuchek, raise your hand, please. Brett is an expert in model interpretability. If you've got questions around that, what we do. Model interpretability is huge now because of bias in AI. We all know, for example, what happened at Amazon and their HR system. It was biased towards males, and they fixed it. So check with Brett on that. I think I'm going to skip the demo given the time that I have. I'm out of time. I'll come back if you have me back. Is that okay? Can I come back? It's been cool. Thank you very much. I'm happy to take a question or two.
Yeah, so while we're setting up for the spotlight talks, anybody have a question?
Got one over here. Sure. Statistics is not dead. Seriously. I'm actually seeing statistics come back. Because, if we really want to do good inferencing, designed experiments and so forth have a lot of value. All this data that I deal with is observational. You just get it, and you get it like a fire hose. And you try to make some sense out of it. Optimization is not dead. It's not used enough. There's always some kind of constraint. I didn't talk about that in the modeling. You develop your model as a data scientist, but then it gets layered with business rules and it gets layered with constraints. What is dead? What else is dead? That's a good question. I think supervised learning is almost dead. I think that the future of machine learning is unsupervised, and there's not good work there. If we want to do real AI and get to general intelligence, this is a table. You can give me 1,000 tables and I can build you a deep learning model and tell you that's a table. But a child understands that's something I could stand on. It's fall off and get hurt. I can get underneath of it. So I think a lot of the supervised learning is just second nature to me. The future is in unsupervised and semi-supervised learning. Thank you.